Okay, I wanted to make a video on the YUPANA, and it is an Andean calculating device that's ancient. It's supposed to be fairly ancient, and it is taught in public schools in Peru, Bolivia, and probably some other countries, but it is taught wrong, and I haven't found any videos that actually teach it the way it's supposed to be, that it's really supposed to be done. It's also called an Incan Abacus. So I'm just going to get right into it. And basically, how you'll see it taught is with the first row here being the ones column, the second row being the twos column, or the tens column, the third row being the 100s column, and the fourth row being the 1000s column, and so on. And I want to make better videos of it later. This is just an introductory video. But when you attempt to do multiplication and division on the Incan Abacus with a decimal system, it is difficult. It doesn't work very well. You end up with piles of, what you use is little rocks. So what they'll tell you is this rock equals 1, and this rock equals 1, this equals 1. So every rock you have on a point there equals 1. And that these three squares all add up to 10, which is true. But what do you do with this dot right here? And then they'll tell you it's a placeholder. And so if you wanted to multiply by 10, you would just move straight up. Anything you want to multiply by 10, you would just move straight up. But, and there's other videos out there that show you how to do it that way. It's taught in public schools in some countries in South America. But it just doesn't work. You can do addition and subtraction on it quite easily this way. And maybe I'll get into showing you later how that works. But I want to show you how I believe and how it appears that this really is done. Now, to give you a little bit of a history on the YUPANA, nobody really has any received knowledge on how it works from any real Incans that used it. And so no one really knows. So there's lots of theories out there on how it works. There's 144 base system. There's several systems, I think 6 to 8 of them, that use a decimal system in one way or another. And I have studied this out pretty thoroughly. Now, what I'm going to introduce to you is a 40 base system. So in the 40 base system, every dot, this dot is going to equal 1. This dot is going to equal 40. This dot is going to equal what is it? Sorry, this is going to equal 1600, and so on. Okay, so every dot that you move up is going to multiply by 40. Now, I want to show you. This is the Mayan system. Now, this system here is somewhat similar to the Mayan numeral system in some way, but it is also similar to the African Mancala system, which most people are familiar with. The game called Mancala, where you move marbles down these holes. What I think almost no one, at least in the Western world, is aware of is that this is an ancient calculating device. It's a binary calculating device. And unless you're somebody that's into computers and or you're a mathematician, you probably don't know about it. But computer programming is done binarily. So in computer programming, I don't know anything about computer programming, but I know what the binary system is. So each hole doubles. And so the amount of each hole is equal to all of the holes behind it and one more. So this hole is equal to these two plus one more. This hole is equal to these three plus one more. So it's actually pretty intuitive and simple. Now, there's no information on the internet that I could find that actually explains how to carry out mathematical calculations using rocks, right? You would have a wooden, it looks just like a Mancala board. You have rocks or marbles in it, and you move them up and down. So every hole you move down divides by half, and every hole that you move up multiplies by half. And it's extremely simple. The only problem with the Mancala system is how it relates to the modern decimal system. The Mancala system is easily written out in octavals. I don't know, maybe I'm not pronouncing it right, but basically it's an 8-based system. So it's actually written out a lot better. It looks nicer. You don't have all this 2,000 and then 48, 1,000 and then 24. It makes it harder to add up. Because we use the decimal system, you have to carry out your calculation. Then you have to convert it from octal, I think it's called octal, to decimals, which takes a little bit of work. And then that kind of ruins the ease of this, because you're going to have a rock left over here, you're going to have a rock left over here, and you're going to have one left over here. So then you're going to add 256 plus 32 plus 4. And that's not that hard, but if you have a whole bunch of holes and you're up into the hundreds of thousands and millions, then it gets a little clunky. Okay, so the YUPANA is also binary, but it does not work on this form of binary where every hole doubles. With the YUPANA, it works on the Fibonacci sequence. Now, supposedly, some guy named Fibonacci in the 1200s in Italy discovered the Fibonacci sequence, which the Fibonacci sequence is similar. It's a little different. Instead of each hole doubling, all the Fibonacci sequence does is it adds the 2 behind it. And so this one, right, the Fibonacci sequence actually starts out with a 1. So it starts out with 2 ones, technically. So the 2 is going to add up to the 2 behind it, right? The 3 is going to add up to the 2 that are behind it. The 5 is going to add up to the 2 that are behind it. So with the Fibonacci sequence, whatever number you're on only adds up to the last 2, right? 21 only is equal to 8 plus 13. 13 is only equal to 8 plus 5. With the binary sequence, which Fibonacci is not binary, the Mancala is binary, and it's because each hole can either be full or empty. Each hole adds up to all the ones behind it plus 1. So having explained that, when this YUPANA is done in a 40-based system, it actually works similarly to the way the Mancala does. But the Mancala is just extremely simple. It's sophisticated for its simplicity. Now, the Mayan system, you can see that it's similar because it has squares, and each square is multiplied a certain amount by a certain amount, right? So, whereas this version is 1, 40, 1600, and 8000. If you look at the Mayan system, and there's a lot of videos out there about the Mayan system, so I'm not going to go into explaining it. It is a 20-base system, so this row of holes equals 1. This each point, right? If you put a rock in it, it equals 1. And the next row is 20 and 400 and so on. So if you're going to do mathematics with the Mayan system, you can see here, 1 dot, 2 dots, and so on, and you can see what the dots and sticks represent. So if I was going to make a calculation, this rock here would represent 1. This stick here would represent 5. That would represent 6. Okay. Now if I put this stick up here into the 20s column, it's going to represent 20, not 1 anymore. Okay. If I put this up there, because this is 5 times whatever that is. Okay. The rock is going to be 1 time whatever that is. And so you'll put one side of the problem here and the other side of it here. If you want to multiply, let's just say we're going to multiply 5 by 2. Excuse me. That's going to be 20. Okay, so we're going to multiply 5 by 20, right? I'm going to move that up here and get rid of that. And you're going to see that the answer is 500. 100. So you can see similarities in the YUPANA, which comes from the Andes Mountains, with both of these ancient systems. The Mayan system is extremely ancient. The African Mancala system is extremely ancient. The Fibonacci sequence is extremely ancient. Fibonacci did not discover it. It's been around forever, and people have been using it to make calculations with, just like a computer. So let's get into this. This is, it's a little bit intuitive. It's something that if you don't understand how it works, you are really going to have to open your mind. And no matter how much you open your mind, you would probably never figure it out without somebody telling you. Now, I'm just going to go into the history. There's some ancient photograph, not a photograph, but a drawing that some medieval conquistador made of a Incan carrying this. If you know anything about a YUPANA, you know the history. In, I think it was 2000, there was an Italian guy. Okay, the picture, this old picture was drawn back in the 1600s or something by some Spaniard. In 2000, after several people had come up with theories about how this works, some guy that was an Italian claimed, his name is Pasquale, and he claimed that in one night he looked at the YUPANA and he figured out that it was a 40-base system. Now, I think that sounds like a bunch of bunk. I don't believe it at all. Was he that much of a genius that he figured it out? It's possible. I think he got the information from somebody else. He read some book that wasn't in circulation. You think about Italy, Rome. The people there might have access to a lot of texts and books that aren't in circulation. So I don't believe the story at all. But when you look at how it works and how much easier it is to carry out calculations instead of being 1, 10, 100, 1,000, when it's 1, 40, 1,600, and 8,000, it pretty much has to be the way that it was done. And this Pasquale guy heard it from someone who understood it. So this is how the layout works in this 40-base system. This point equals 1. Each point in this box equals 2. And the entire box equals 4. You can see right here, wrote down in the corners, the point is 1. The entirety of the box equals 1. Each point is 2, but the entire value of the box is 4. In this box, each point equals 3, and the entire value of the box is 9. In this box, each point equals 5, and 25 is the entire value of the box. Now, if you add up 25, 9, 4, and 1, you get 39. So you have to add one more, and you get 40. So if you fill this whole entire box up, the value of this whole entire row, the value of it is going to be, how long?
Yeah.
So you can see the whole entire value of the box is the value of each point added up, right? So this dot here is the value of all these dots behind it plus one more. So it's using the Fibonacci sequence. It's using the Fibonacci sequence of 1, 2, 3, 5, 8, 13, and so on, right? 1, 2, 3, 5. But just like the Mancala system, each dot here equals all of the dots behind it and one more. So here you move on. Each dot equals 80. The whole entire box equals 60. Now you can see how it works. 360. Each dot equals 120. Each dot here equals 200. The entire box equals 1,000. Okay, so you add up this entire row and this entire row. You're going to have, the total is going to be 1,599. You're going to have to move up one more. I'm just going to make 1,600. So on each one of these points, if you want to multiply by 40, you just move up one. It's real simple. And it's the same thing with the boxes. If you want to multiply by 40, you just move up one. And so normally, the way it's shown that you divide and multiply, there's going to be all these rocks like here and over here, or they're going to have like over here they're going to have all kinds of rocks piled off. Over here you can't see them to keep track of your calculation, because the value of each hole is only worth 1, and you can hardly do anything with it. So what we want to do is learn how, we know the layout with a 40-base system, but we want to learn how to carry out calculations. So it's a little bit more complicated than the Mancala or the Mayan method.